This is selective precipitation. What we have here is a beaker that contains silver plus, Pb2 plus, and mercury 1, Hg2 2 plus ions. And all of these are at the same concentration, 0.0015 molar. And what we're doing is we're adding some sodium chloride solid so that gradually the concentration of the chloride ion is increasing. And because of the relative KSP values, one ion, then the other, then the third is going to precipitate out as the chloride. All of these are insoluble chlorides, yet we can still separate them because they have different KSP values. Okay, now we're going to do some calculations to see why that is the case. So we're going to find out what the concentration of the chloride ion is when each salt just begins to precipitate, or in other words, when it is at equilibrium. So we can write out the equilibrium expression for all of these. And remember this weird mercury ion, the mercury 1 ion, is a little strange as it's essentially 2 atoms of mercury with a net charge. And then we get 2 chloride ions. So in each case we can set IP equal to KSP and determine what concentration the chloride ion needs to be in order for that system to be at equilibrium. So we'll take these each in turn. Alright, we're going to be solving for the chloride ion concentration because we know the KSP and we know the lead 2 plus. All of these metal ions have the same concentration, 0.0015. So initially we solve for Cl2 squared. That's going to be KSP divided by the concentration of the metal ion, Pb2 plus. But since we want just Cl minus, we're going to take the square root of all of that. So we have Cl minus is going to be equal to KSP, which for this compound is 1.7 times 10 to the minus 5 divided by 0.0015 square root. And we find the Cl minus ion concentration is 0.1065 molar, or with 2 sig figs, we see Cl minus has to equal 0.11 for the system to be at equilibrium. And we'll do the same thing for these other two. We're going to solve for the chloride ion in the KSP expression. Finally, for the mercury 1, Again, we want Cl minus ion concentration, so we're going to take the square root. KSP here. Okay, so we have the ion concentration within 2 sig figs for each of these metal ions in solution. So these are the concentrations of the chloride ion that have to exist for each one of these ions to be in equilibrium with its chloride. Alright, so let's look at the second question. Okay, so what concentration of the chloride ion must be present to precipitate as much of the Hg2 plus as this solid, this is our precipitate, and without precipitating either of these two ions. So let's think about this. So as chloride ion concentration increases, okay, the first one of these to precipitate out, the first compound to precipitate is going to be the mercury 1 chloride, because it requires the lowest concentration of chloride ion to be at equilibrium. So that's going to precipitate first, and this starts when the chloride ion concentration is greater than 3.1 times 10 to the minus 8. So this is where we're at equilibrium. If we increase the chloride ion concentration, IP is going to be greater than KSP. And therefore we're going to get a precipitate. Okay, but we don't want to stop there, because we want to remove as much as possible. So we continue adding NaCl. And as we continue adding NaCl, Hg2, Cl2 will continue to precipitate. And as it's precipitating, it is removing Hg2 2 plus ions. So the concentration of this ion in solution is decreasing. We're removing it. The ions are being removed as this solid. Okay, so we continue adding to NaCl, so the chloride ion concentration, when it equals 1.2 times 10 to the minus 7, your AgCl is at equilibrium. It's a saturated solution. So we want to stop, because if we continue increasing the chloride ion any more at this point, we're going to start precipitating out silver chloride. So we want the chloride ion concentration as high as possible so that we remove the most amount of mercury 1 ion, but we do not want AgCl to precipitate. So what we do is we set the chloride ion concentration equal to 1.2 times 10 to the minus 7, and we're done. So as much of Hg2 plus as possible is going to precipitate out, and yet AgCl and your lead 2 plus, or your Ag and your lead 2 plus will remain in solution.